Hi, welcome to our presentation, the final design video of the Automotive Design Project Energy Challenge. We are Group 1, and since I'm the communication manager of this group, I will start with a short introduction. Well, first of all, the background of the project. We are working with Eindhoven University of Technology for a company called TUE Vehicles. And they are a progressive vehicle manufacturer who have recently created their first electric vehicle. And they have given us a 1 in 5 skill model to perform tests on to see how efficient it is. The specs of the vehicle are as follows. First of all, it's controlled by remote, of course, since it's a remote controlled car. It has a 780 kilovolt electric motor, which is powered by a 22.2 volt lithium-ion battery. The motor has a maximum angular velocity of 30,000 rotations per minute, or RPM. During the challenge day, the car will be powered by the battery, as I just mentioned. However, while testing the car, we had to work with power adapters, which we could plug into the wall socket for energy. Then the motor speed is controlled by an electronic speed control unit, or ESC, which is powered by the same battery as the motor during challenge day. Then there is an Arduino on the car as well, which is powered by a separate 7.4 volt lithium-ion battery. The Arduino is used to calculate the speed using an RPM sensor that's on the car as well, and to display the speed on the LED strips, which will be mentioned later in the presentation. Then there is also a voltage regulator, and during the final challenge day there will be a watt meter installed on the car, which will measure the amount of energy in watt hour that the car uses during the drive. And then that value will be compared to the value that we have calculated. Well, the problem statement. The goal of this project is to define an optimal energy efficient driving strategy. And to do that, we had to perform a lot of tests first of all, to calculate and to measure the environmental effects on the car. First of all, a wind tunnel test was done to calculate the aerodynamic drag force on the car. Then second, a rolling resistance test was done to measure that force. And thirdly, a dynamometer test was done to calculate and measure the power losses and efficiency of the car. This will all be explained later during the tank to wheel part of this presentation. And so with all the results that we got from the test, we have done all the calculations. Then there was the problem of displaying the speed using the LED strips on the car, which will be mentioned after this as well. And lastly, the driving strategy had to be determined, and that will be covered last in this presentation. And all our findings will be tested on the challenge day and will finally be written down in our final report. Well then, our group, we consist of 7 members, and to make the workload a little bit more manageable, we divided ourselves into subgroups which worked on a different part of the project. And to do this, we had to work together a lot, and we had to keep each other updated on everything, since we all have to know what's going on with each subgroup. So we did it by having weekly meetings with our supervisor, and that we discussed all the problems we were facing, and we presented our results with each other, and that way we could help each other to reach the end goal. And that was our way to deal with the amount of work. And also what was very important for this project was a good planning. We had to work systematically to make sure everything was done in time, since there were a lot of deliverables and almost every week something had to be delivered, had to be handed in, and to do this, a proper planning was crucial. Then the content of this presentation will be as follows. First of all, Kevin will talk about the tank-to-wheel analysis. Then I will elaborate on the speed measurement system, and finally Bengt will give his presentation on the optimal driving strategy. So I will now give the word to Kevin.
Well, my name is Kevin, and today I'll be presenting the tank-to-wheel analysis. So, quick overview of what I'm going to be presenting. So, first, the goal of the tank-to-wheel analysis, then an overview of the rolling resistance, aerodynamic drag, dynamometer tests, and finally an approach and results of the tank-to-wheel analysis. So, first, the goal of the tank-to-wheel analysis. So, in order to define a goal for the tank-to-wheel analysis, a goal of the project has to be defined. And that goal is to develop an optimal energy-efficient driving strategy. But in order to do that, we have to find the optimal velocity. And that is the goal of the tank-to-wheel analysis. And in order to find the optimal velocity, a road load force has to be computed, but that will be shown in the approach and the results. So, first, the rolling resistance test. The goal of the rolling resistance test was to find the force due to rolling resistance. Now, how was this done? Well, a slope was taken to initialize acceleration, then a flat surface was used for the rollout phase. The deceleration during that rollout phase was then measured. So, the approach for the calculation was as follows. So, the total force on the car was computed, which is equal to the mass of the car times the acceleration of the car. This was equal to the force due to rolling resistance, the aerodynamic drag force, and the force of the motor resistance. This equation was rearranged, and in the end, a force of the rolling resistance of magnitude was found, and that was found to be 2.855 newtons. Then the aerodynamic drag test. For this test, the goal was to find the aerodynamic drag force, and this was done by calculating the drag coefficient and the aerodynamic drag force for different setups and velocities. Now, the following approach was used. So this equation was then used to calculate the aerodynamic drag force, and this composes of the air density, the aerodynamic drag coefficient, the area or the frontal area of the car, and the velocity in meters per second. So in order to find the frontal area of the car, a picture was taken of the car and a grid was placed on it to create an estimation of the area. This area turned out to be 6.68 times 10 to the power minus 2 meters squared. Then the drag coefficient had to be found. Different setups were used, and eventually the most efficient setup, which turned out to be only using the front splitter, gave a drag coefficient value of 0.98. Then for the dynamometer test. The goal of this test was to evaluate the efficiency of the total system and the efficiency of the powertrain. Since the tank-to-wheel analysis only uses the efficiency of the powertrain, I will only talk about that. So the following equation was used to calculate the powertrain efficiency. This equation was then redone for different velocities and different loads. And then these different data points were interpolated using MATLAB, and an efficiency map was created. This is the efficiency map that was created, and it can be seen that at the highest velocity and at the highest load, the so-called sweet spot of efficiency map can be reached. Now, for the approach and the results of the tank-to-wheel analysis. So, for the approach of the tank-to-wheel analysis, first the force road load had to be computed. This consisted of the aerodynamic drag force and the force due to rolling resistance. Of course, the force due to slope is omitted, as this was not tested. Now, this force road load was computed for different velocities, and with a combination of the powertrain efficiency map, an energy per meter graph was created. Now, from this graph, it can be seen that at the lowest energy per meter consumption, a velocity of 4 meters per second existed, and this was then taken as the optimal velocity. Well, to summarize, a force road load was computed using the aerodynamic drag and the force due to rolling resistance. Then, in combination with the powertrain efficiency map, an energy per meter graph was created to find the optimal velocity. Well, that concludes the tank-to-wheel analysis, and now my colleague will continue with the speed measurement system.
Yeah, I will tell you about the speed measurement system. So first of all, like I mentioned before, on the car there is an Arduino and a cog wheel with two magnets on it with an RPM sensor. and that sensor sends a pulse to the Arduino, so a high voltage, each time a magnet passes it. And when that pulse reaches the Arduino, the running time of the code is saved into a variable. So after 2 pulses have been received by the Arduino, we can calculate the time interval between those pulses, and with that we can calculate the velocity of the vehicle. This was done using the following formula. The formula is 1/3 times a half times the circumference of the wheel divided by the time interval. The 1/3 comes from the gear ratios, since the engine turns at 3 times the velocity of the drive shaft, and the 1/2 is because of the time interval between 2 pulses is only half a rotation, since there are 2 magnets on the cogwheel, and that's why it's in the formula. Then the next problem was controlling the LEDs. There are 4 LED strips on the car. On each side there's one, and on each of the strips there's one driver with a 96-bit register on it. So it has 96 bit, and each bit controls one diode. There are 32 lights on the strips, and each LED consists of a red, green and a blue diode. So if the bit that controls that specific diode is 1, then it emits light, and if it's 0, then it's turned off. So to control this, we had to firstly control the clock, and each time the clock went from a low to a high pulse, then all the bits in the register were shifted to the right once, and we could input the leftmost bit, so bit 95 in this case, and by doing that we can change the order of the lights that are on, and that way we can change the color of the LEDs. So to change 96 bits, so to change the entire LED strip, first the latch was turned on, so that's kind of the switch of the lights. It has to be turned off, and then 96 bits have to be inputted, and then the latch has to be turned on again, and then all the lights change color. So for instance, if this is the input that we sent to the driver, then all the lights emit a blue color, and if this is the input, then all the lights emit a purple color. So then our display strategy, the driver during challenge day has to know how fast the car is going. So by using the velocity that we had calculated with the RPM sensor and the LED control that I just mentioned, we thought of a strategy to display the speed best, and that is by changing 8 LEDs per 1 km/h speed difference. So if the car goes 1 km/h faster, then 8 bits change, and therefore 8 LEDs change. So like this, from one side 8 bits change, of 8 LEDs change, and then 8 LEDs change again. So this goes on until the optimal speed of 4 meters per second is reached. Then all the LEDs are green. So then when you drive a little bit slower than the optimal speed, then it will change again from one side, and if you drive too fast, then it will change again from the other side, and therefore the driver can know exactly if he's going the right pace or not. Well, this concludes my part on the speed measurement system, and I will now give the word to Bengt for the last part of this presentation.
Hello. Today I will be talking about the optimal driving strategy for the energy challenge. So I'm going to talk about what the goal is of the optimal driving strategy, the way we're going to drive to the drive line, the acceleration and deceleration that we're going to use, how the tank-to-wheel analysis led to the optimal driving strategy, and then the energy estimate for the total track that we're going to use on the Energy J challenge. So the goal of the optimal energy is to find the optimum efficiency. That means knowing the right velocity, knowing the right acceleration, and knowing the steering angle that you're going to use for the track, basically. So what we did first was we calculated the maximum acceleration or velocity in the corners using these formulas. So this is the centripetal force, which is the mass times velocity squared divided by r. Then the static coefficient for friction, which is the coefficient of friction, or static friction, times the mass, times g, which is 9.81. So the, what do you call it? Gravitational pull, basically, which is 9.81 meters per second squared. And then you can put them together for this formula, which is the velocity, which is the square root of the coefficient of static friction, times g, times the radius of the turn. Let's see. And so none of these values that we got for the cornering speed or velocity were higher than or lower than 4 meters per second, which was the optimal velocity. So we didn't need to worry about slipping in the corners or driving too fast, that we wouldn't reach the optimal efficiency for the drive. Then for the acceleration, what we did was we used 2 meters per second squared, as this was found to be optimal for the motor, which was at about 75% efficiency when used at 2 meters per second squared, the acceleration. And then we used these numbers, or these equations, which is the change in velocity is the acceleration times time, and the distance is the velocity times time plus a half the acceleration times t squared. And this got us basically where we needed to accelerate and where we were on the track at what given time, which would help with the optimal energy estimate. And then we got the deceleration by using the tank-to-wheel analysis, which gave us a resistive force of 6 Newton about, which I had to divide by the mass of the car, which eventually gave you this number, which is 0.52 times meters per second squared. And then we have the total power consumption over the track, which we used the optimal velocity force of 4 meters per second squared, and also a different part of the tank-to-wheel analysis, which gave us the optimal efficiency, or the efficiency per meter, over the total track, so times the distance. So to conclude the whole presentation, the tank-to-wheel analysis gave us the optimal velocity of 4 meters per second. 4 meters per second. The speed measurement system used 8 LEDs per kilometer to give a change of speed. So 8 LEDs would change per kilometer change, really. So and the optimal efficiency, or the estimate for energy used, was 1890 joules for the total track. This was our presentation, and thank you for listening.
Deze duurt een stuk langer.